The last ideal topology that we're going to consider is our Shunt-Shunt topology, or our trans-resistance amplifier. So it's called our trans-resistance amplifier because we have a current as an input and a voltage as an output. And so just like with our series configuration, we're not going to delve too deeply into the analysis because in most cases it's going to be pretty similar to what we've seen for our voltage and our current amplifiers. We are going to point out, though, that based on this first sort of initial circuit where we see our shunt connection on the left and on the right, or rather our parallel connections, we can expand this basic amplifier to include an input resistance, an output resistance, and then we have this gain element represented by our dependent voltage source. Same thing with our feedback network. So we have our feedback network here, beta sub G, and we can represent that here with this dependent current source on the right. And we note that we have an infinite input resistance for our feedback loop just to reduce loading effects on our output. So for our feedback loop. We also have our output open circuited the same way we did when we looked at our voltage amplifier. And so we are not going to go through the analysis for finding our transfer function, but I do have that analysis in Canvas and it's also in the textbook, so if you're interested you can look there. And then for our input and output resistances, because we have already considered these configurations, or not this particular configuration, but we've considered a shunt input when we looked at our current amplifier and a shunt output when we looked at our voltage amplifier, the same results are going to hold for our input resistance and our output resistance. Okay, so if we had gone through the analysis for our transfer function, what we find is that our closed loop gain is A sub ZF, which is equal to A sub Z, which is our open loop gain, divided by 1 plus beta G times A sub Z. And so this is equal to our output voltage divided by our input current. And so because it's our voltage divided by our current, we can call this our closed loop voltage to current transfer function. So closed loop voltage to current transfer function. And so again, we see a slightly different beta than what we've seen before. So now we have this beta, sorry, not beta Z, beta G, which is our conductance feedback transfer function. So again, we have a slightly different beta depending on which type of amplifier we're looking at. But we see we have the same basic form for our closed loop gain regardless of what amplifier we're looking at. So because we have our shunt input, we can compare that to when we looked at our current amplifier, and we can get a input resistance. So because we have the shunt input, our input resistance is given by R sub I, the input resistance to our open loop configuration, divided by the quantity 1 plus beta G times A sub Z. And because we have a shunt output, we've already analyzed what happens when we have a shunt output when we looked at our voltage amplifier, and we saw that in that case our output resistance with feedback is equal to the output resistance without feedback divided by the quantity 1 plus beta G times A sub Z. And so in this case, we see that both of these values are decreasing compared to before adding feedback. And so just like we have seen with all of our previous configurations, this is going to be desirable. And so to sort of highlight that, we can look at our equivalent circuit down here. And so like before, let's highlight sort of inside our feedback network with amplifier in this green area here. So inside the green represents our feedback network amplifier, so all of that stuff combined together. And so we notice that we are decreasing our input resistance. So we have a small value for RIF. And so qualitatively, remember, current is going to want to take the path of least resistance. So as this value gets smaller, that means more of this input current, which is flowing here, is going to be continuing into this RAF value. And so that's good because that means we're losing less current to this source resistance RS. On the output side, we said we're also decreasing this ROF, so we're decreasing this value here. And so that's also good because from our voltage divider, we know that the smaller the value of this resistor, the less of this output voltage is going to be dropped across it. So that means our output voltage Vout is going to be more similar to this value of the dependent source. Another way of saying that is that Vout is going to be less dependent on this load resistor, which again is a desirable thing for all of our circuits. So that sums up our 4 basic ideal topologies. So there's actually a really good summary table in the book, and so I'm going to have this posted on Canvas as well. But if you look on page 872 in the textbook, you'll see a table that sort of summarizes the transfer functions, the input resistance, the output resistance, the input signal, and the output signal for all 4 of these topologies. So I highly recommend you take a look at that as you're studying. And as of course, if you have questions, please don't hesitate to let me know.